In our previous lesson, we have learned that a well-defined collection of objects is known as set. We have also learnt methods of representing the sets along with some basic definitions. In today's lesson, we are going to compare two sets and develop the idea of equality and one set as subset of the other. Now, let us consider two sets P and Q. The set P is containing 4 elements 2, 4, 6 and 8, and the set Q is containing numbers 1, 2, 3 up to 9. What we observe that all the elements of set P are included in set Q. Symbolically, we can say that x belonging to P implies x belongs to Q. In such cases, we say that set P is contained in set Q because we observe that all the elements of P are in set Q. We write it as P contained in Q. This symbol is for contained. Now, let us include one more element in set P. Now, set P will be having 5 elements 2, 4, 6, 8 and 10 and the set Q remaining the same. Now, what we observe? We observe that only 4 elements of set P 2, 4, 6, 8 are in set Q, but the additional element 10 of P has not been included in the set Q. We say that P is not contained in Q, or we write it like this: P not contained. The symbol is not contained in Q, or when P is contained in Q, we say P is subset of Q. When P is not contained in Q, we say P is not subset of Q. So, the definition of subset can be given as a set A is said to be subset of set B if every element of set A is also an element of set B, as we have earlier seen. Symbolically, we will write x belongs to A implies x belongs to B, then we say A is contained in B or A is subset of B, and this information can also be written as B contains A. B is superset of A and A is subset of B. What we have learnt now? If x is an element of A and it implies x is the element of B, then A is contained in B. Again, if y is an element of B, it implies y is an element of A, then we say B is contained in A. Here, what I am telling? A is contained in B means all the elements of A are in B. Then I am telling B is contained in A. All the elements of B are in A. That means A is having all the elements which are in B and B is having all the elements which are in A. So, we can conclude that A is equal to B. Here, the definition of equality can be generated. Two sets A and B are said to be equal if and only if A is contained in B and B is contained in A. Again, if we have an element x belonging to A, it will positively be in set A. Any element, if it is in set A, it will be in set A. So, in mathematical language, symbolically, we can write x belongs to A implies x belongs to A. That means, the set A is subset of itself. So, we can conclude that every set is subset of itself. Empty set is subset of each set. Now, so far we have used two symbols, belongs to and contain. Let me clarify these two symbols once again. Let me consider the set A containing 3 elements. The elements are 1, and this set containing 2 elements 2, 3 is the element of the set, and third element is 4. See, this is the element of the set. So, this will belong to the set and this symbol will be used. Again, if I put this element within braces, then this will be a singleton set, and this set will be the subset of the set A. Similarly, 1 is the element of set A, so it belongs, and 1 put within braces is a set which is the subset of set A. Let there be 2 sets A and B such that A is contained in B and B is having at least one element extra. Then A is said to be the proper subset of B and B is called the superset of A. For example, let X be having 5 elements L, M, N, O and P, and set Y is having all the elements which are in X and one additional element. Then X is the proper subset of Y and Y is known as superset of X. We can say if A is equal to B, each is improper subset of the other, because in that case A is contained in B and B is not having additional element. Similarly, B will also be the improper subset of A, and also each set is improper subset of itself. Now, let me consider a set having 2 elements A and B. We have learned what do we mean by subset, and we have agreed that empty set is subset of each set. So, phi will be the subset of set A, number 1 subset. Then this is having only one element which is included in A. So, 1 subset. This will also be subset, and each set is subset of itself. So, this will also be the subset of the set A. Let me have the collection of all the subsets. Then this collection, all the elements will be written here as we have learnt in our previous lesson within braces, and it is the set of all subsets. This set of all subsets is defined as power set. Let A be a set having only one element, then power set will be having 2 elements, phi and this singleton set as we have just learned. Number of elements in set A is 1, number of elements in power set is 2. Again, set A is having 2 elements, one additional element has been put in this set. Now, number of elements in set A is 2. Power set will be having 4 elements, we have just discussed. Now, number of elements in power set is 4, which can be written as 2 raised to the power 2. Now, one more element has been put in set A. So, there are 3 elements in set A. Power set will be having these elements phi, singleton sets, sets having 2 elements and the set itself as earlier we have discussed. So, total how many elements in the power set of A? We have got 8 elements. Let me list this information in the form of table. Here I have listed the number of elements in the set A and here number of elements in the power set. We find that the relation is number of elements in the power set is equal to 2 raised to the power m, where number of elements in set A is equal to m. Now we come to a very important point. Whenever we discuss problems including sets, there is always a set which contains all the sets which are being considered for that particular problem. This superset, which is having all the sets under consideration as its subsets, is known as universal set. Suppose we are considering set of integers, set of prime numbers, set of natural numbers, then set of real numbers can be considered as a universal set, or set of integers can be considered as a set of universal set. Only thing, universal set is the set which is the superset for all those sets which are being considered for that particular problem. Now, let us consider subsets of real number. Let me take two real numbers a and b, a less than b, and plot them on the number line. Now, let me consider the set of all real numbers such that the real number is greater than a and less than b, a and b not included. Then it represents an interval which is known as open interval. Open interval is written like this. Suppose we want to include numbers a and b. Then in set form, we will write it as set of all x such that x is a real number, x is greater than or equal to a and less than or equal to b. This set is represented by closed interval written like this. A was not included, hollow circle. B was not included, hollow circle, and in between portion is darkened. Now, let me consider the set of all real numbers such that the real number is greater than a and less than or equal to b. What does it mean? A has not been included in the set, whereas the number b is included in this set. So, how do we write this interval? This interval is open on the left and closed on the right. Let me come to the set of real numbers where x is greater than or equal to a and less than b, means a has been included and b has not been included. Again, a is on this side closed because a is included and the circle is dark. B has not been included, so here we have drawn the hollow circle and the portion in between is darkened. B minus a is known as length of the intervals. Now look, here is a very important point. These are all four finite intervals, but are having infinite number of real numbers. So, we can say that these intervals are finite intervals, but infinite sets. In our next session, we are going to learn some operations on sets, and we will be learning Venn diagram and see how Venn diagrams make our study of set theory very easy and interesting. Thank you.